So thank you for coming today on this happy Halloween. Basically, today's presentation is going to have a interactive component, a component where I'm going through some regression trees and classification trees in R, so you could have some take-home knowledge, and then a very brief segment in the beginning about the theory and the background. So let us begin. As you can see, statisticians and machine learners like to draw trees upside down. You'll see why in a moment. So I'd like to start off by first knowing, what do you already know about decision trees and this approach, so I don't repeat myself. Anybody seen one before? Okay, a few have seen some. Have anyone done any analysis with random forest before? Some? Okay. Okay. All right. And does anyone know why these things are useful, if at all?
They're extremely flexible, and you don't have to worry about any assumptions.
Okay, flexible, not worrying about assumptions, easy to interpret in many cases. Okay, good. These are all excellent things. So one technical definition, if you will, is the following. But what does that mean? What is a prediction space? How do you break these things down? And what are splitting rules? So to give you a up-to-date example, say this were your image, and you want to create some sort of splitting rules to divide this predictor space into simple regions. You might do this. You might say, if anything falls in region 1, I'm going to call it the left eye. If it falls in region 3, I'm calling it the right eye, and so on and so forth. So these are splitting rules, simple regions, predictor space. Now, one thing you may notice is if the data are different the second time, you may get a completely different set of splitting rules. So even though these are both strangely deformed pumpkin men, the decision rules are different, the regions are different, you can see. Okay, but these are fake life examples. I'm going to give you a real life example. How many of you have heard of Ebola? So this is a decision guide or algorithm, a decision tree algorithm to know your outcomes of interest are yes, test the person, optional test, or no test. And based on the criteria, did the person participate in funeral rites involving the body? If so, do this. Do they have a fever? Yes. If no, et cetera, et cetera. So you can see how you can use these in real life. There's no normality assumptions here, as you said. It's just some splitting. So anyway, I would like you to get some experience and practice in creating your own set of splitting rules. So the goal is predict if someone will go to a Halloween party. And in your rows, I want you to come up with like 3 to 5 questions. And you can't be that direct. You can't ask, are you going to a Halloween party this year? So anything else is pretty much okay. So I'll give you like 3 minutes to do this. So have fun. And I'm going to write down the good ones. Okay, excellent, excellent. So basically, I would also add, were you invited to a Halloween party? That. So I will argue, what you just did is, in a way, you kind of started getting towards a random forest. So let me explain why I feel this way. What are random forests? So it's a method, ensemble method, where you get different decision trees, in a sense, and you combine their results to get somewhere. Now this is very vague, so let me first break this down into 2 steps. Say the first row and the second row and the third row, they all asked a different set of people in this room, let's say, or in this school or in this building or whatever. That would be different subsets of the same data, maybe. Number 2, different sets of predictors. So the first row may ask some of these questions, the second row may ask some different questions, but basically these are all subsets of a larger number of predictor questions. How many of you know how to do this first thing? What do you call this? You only have one data set, but you somehow get different subsets of it. What is that called? Bootstrapping. Okay. So this is a allusion to the matrix in a sense, but you got some data. Bootstrap 1, you get some randomly selected versions of it, et cetera, et cetera. You get different bootstrap samples, and they each came from the same data, but they're not the same data. Now, there's one assumption I'm making here that may not necessarily be true always. Notice I'm only capturing O once, so I'm sampling without replacement. There are bootstrapping where you sample with replacement as well. So anyway, the more interesting thing is going back to all these questions. So say there were 12 questions. The first part may only ask a subset of them, Q1, 3, 5, 8, and 11. Different decision trees, I guess, in essence, are looking at different questions. And you combine this approach, where you get different parts of the data, different predictors, and then you combine the results in some way. And again, I'm being very vague, because I haven't really talked about what kind of decision trees we're looking at. What are our outcomes? If our outcomes are classes like yes, screen for Ebola, optional, or no, then this is more of a classification tree. If your outcome is something with regression where there's a continuous outcome, then you do a different method. So anyway, I'm going to actually show you a real example so we don't have to dwell on this. Again, I haven't told you by what criteria are we splitting up Mr. Pumpkin Man. How did we determine that these are the best ways to do it? So there's some keywords, there's a Gini index, there's something about cross entropy. I'm not going to cover these, but for your own interest, I will leave that to you. Okay. And again, the good news and bad news of this method. Easy to interpret. It's nice to be able to have not many assumptions. You're going to see these two things in the R application part, where you change the input data a little and you get different results. Kind of like this. Change the data, different regions. So that's one disadvantage of a decision tree. The advantage, again, being it's relatively straightforward to interpret. And if you want to do this at home, get these two packages. There are many. Remember the capital F. The other one doesn't exist. OK. And these are things that I'm not going to talk about. Unfortunately, that would have to be another lecture.